In the vast and dark stretches of the universe, where even light struggles to travel, humanity has built a machine capable of peering deeper into the cosmos than ever before. The James Webb Space Telescope, launched in December of 2021, has become our ultimate eye in space, unveiling secrets hidden behind dust clouds, time, and unimaginable distances. But among its many discoveries, one in particular has stunned the scientific community, a star that, by all understanding of astrophysics, should be dead. And yet, it lives. Imagine a star going through the violent cataclysmic end that marks the conclusion of its life, a supernova explosion. A bright burst of energy more powerful than anything else in the galaxy for a brief time, signaling that a massive star has exhausted its fuel. Normally, such an explosion results in a neutron star or black hole, depending on the mass. The star as it once was is gone, destroyed in the process. But now, thanks to Webb, astronomers have witnessed something that challenges that rule, a star that exploded and somehow still remains. To grasp the magnitude of this discovery, let's rewind for a moment. The James Webb Telescope isn't just a bigger, fancier version of the Hubble. It's tuned to see the universe in infrared, allowing it to peer through cosmic dust and capture ancient light, stretching back more than 13 billion years. This means it can observe phenomena from the early universe, but also in more detail than ever before. In its latest observation campaign, scientists turned Webb's gaze to a distant galaxy hosting a strange stellar remnant. They expected to observe the aftermath of a long-dead star, a supernova remnant, likely a neutron star or a newly formed black hole. Instead, what they saw was a bright, pulsating source of light where there should have been darkness. Something was emitting energy, not the slow fade-out of a dying object, but the active, sustained power of something alive. And here's where things get wild. This wasn't just any light. It had characteristics that suggested the presence of a star, still burning, still active, still somehow whole. This led scientists to a stunning hypothesis. Could this be a star that survived its own supernova? The idea isn't entirely new in theory. Astrophysicists have speculated about stars that could undergo a partial supernova, shedding much of their outer mass in a violent event, but retaining a core capable of reigniting. But no such object had ever been directly observed until now. The star in question, buried deep within its galaxy and billions of light-years away, appears to defy the conventional death sentence of massive stars. Its light signature was first noticed when Webb scanned the galaxy cluster it resides in, and follow-up analysis suggested this was no ordinary stellar remnant. The light curve, how its brightness changed over time, didn't match the expected decay of a supernova. Instead, it showed fluctuations consistent with an active star, potentially one still undergoing nuclear fusion. Astronomers nicknamed it the immortal star. While poetic, the name reflects the deep scientific mystery behind its survival. One theory is that this star had an unusual composition, possibly rich in certain elements that allowed its core to avoid total collapse. Another possibility is that it was part of a binary system, and the gravitational dynamics between two stars affected the explosion in such a way that part of the primary star was shielded or even stabilized by its companion. Still, none of these possibilities are fully confirmed. This star is rewriting the rulebook, and no single theory yet explains everything Webb is seeing. The telescope's instruments detected strong hydrogen emission lines, unexpected for a supposed stellar remnant. Typically, hydrogen is ejected in a supernova and dispersed. But in this case, it looks like the hydrogen is still being burned. That points to ongoing fusion, the fundamental process that powers stars. If this star truly survived its own death, it could change how we understand stellar evolution, especially for stars of extreme mass. Normally, stars several times more massive than our Sun burn fast and die young. The more massive the star, the shorter its lifespan, due to the immense gravitational pressure forcing faster fusion. When the core runs out of fuel, it collapses under its own weight, triggering the explosion. But this case suggests there might be exceptions. Stars that hover are right on the edge of this critical mass, or that possess unusual magnetic fields or rotational speeds, might undergo a different fate. Webb's ability to see in the infrared is the key to this discovery. Visible light would never have picked up the object behind the clouds of gas and dust. Only infrared can slice through these cosmic curtains and show what's hidden. And what's been revealed might be just the first of many such anomalies waiting to be found. If immortal stars are more common than we thought, it could require a complete re-evaluation of how we model stellar life cycles. There is also a deeper implication. The life and death of stars is a central part of how the universe recycles matter. Elements like carbon, oxygen, and iron, the building blocks of life, are forged in the hearts of stars and spread across space when they die. If some stars don't die in the expected way, how does that impact the distribution of those elements? Could it affect how galaxies evolve? Could it even shift our understanding of how planets form, or how often life-friendly conditions appear? The answer might lie not in a single star, but in the patterns. Webb's ongoing mission is capturing light from galaxies billions of years old, showing us the universe in its infancy. By comparing those distant ancient stars to ones like the immortal star, we can begin to map out how the rules of stellar death have changed, or not, over time. And here's another twist. This isn't just about one outlier. Since detecting this unusual star, astronomers have begun identifying other candidates. While none are confirmed yet, the very idea that Webb could uncover more stars that survived partial supernovae suggests that this is more than just a fluke. We may be on the brink of discovering an entire new class of stellar objects, beings of fire and gravity, that bend the rules of life and death as we understand them. Some astronomers have drawn comparisons between this star and a hypothetical class of stars known as zombie stars. These are celestial objects believed to have died in a supernova only to return, reignited in some form, still active against all odds. The term was originally used more metaphorically, but in light of Webb's findings, it's becoming a scientifically relevant concept. If a star can shed its outer layers violently and still retain a functioning core capable of fusion, it would indeed resemble the concept of a star rising from its own ashes. The process that could allow this to happen is thought to be extraordinarily rare. A typical supernova is so energetic that it disrupts the star entirely. But if certain conditions align, say the explosion is asymmetric, or if the core is unusually dense and tightly bound, it may be possible for a part of the star to endure. It might also relate to how quickly the collapse happens, or whether rotation plays a role in maintaining stability in the aftermath. High-speed rotation can delay or redistribute the pressure building at the core, altering the dynamics of the explosion itself. There's also a more exotic idea under consideration, that this star may not be entirely natural in its survival. While still speculative, some theorists have proposed that advanced civilizations might be able to manipulate stellar processes on a massive scale, perhaps to preserve energy sources or stabilize their environments. While there's no evidence for artificial interference here, the sheer strangeness of the observation leaves room for wild possibilities. Until more data comes in, no theory is off the table. In practical terms, astronomers are now using Webb to revisit other supernova remnants across the cosmos, particularly those with unexplained energy emissions. There's hope that similar patterns of infrared radiation, especially those indicating persistent hydrogen fusion, might be found. If multiple examples can be documented, it would confirm that this is not a one-time event, but a previously undetected stage in stellar evolution. This discovery has also led to renewed interest in the early universe. Webb has already spotted galaxies forming less than 400 million years after the Big Bang, and these environments were home to the very first generations of stars, population 3 stars. These were massive, metal-poor, and short-lived, and none have ever been directly observed. If some of them had the potential to survive supernova-like events, it could change our assumptions about the chemical enrichment of the early cosmos. Surviving stars would not only continue burning, but might even recycle some of the ejected material, drawing it back in through gravitational pull. This would mean that they contribute to the interstellar medium differently than previously thought. Instead of a clean break, explosion, dispersal, death, there might be a loop. A cycle in which stars are maimed but not destroyed, wounded but still functional, existing in a half-life where the past and future of stellar evolution blur. Even more intriguing is what this might mean for neutron stars and black holes. If some massive stars survive their own explosions, it suggests a missing population between standard stars and collapsed remnants. It raises the possibility that we've miscategorized some objects or failed to recognize subtle signals indicating survival. Some neutron stars might, in fact, be half-dead, cores of stars that only partially collapsed, still burning in some obscure layer hidden beneath a crust of exotic matter. The implications stretch into cosmology, too. If stars like this are more common than we thought, it might influence the way we measure distances and time in the universe. Astronomers use certain types of supernova as cosmic yardsticks, standard candles, to determine how far away galaxies are. But if those explosions don't behave consistently, it could introduce errors into our calculations, or at least call for a revision of existing models. The immortal star, as mysterious as it is, could also shine light on dark energy and the accelerating expansion of the universe. If we're misinterpreting the brightness or behavior of supernovae due to survivors hiding in their remnants, our entire understanding of cosmic acceleration could be subtly skewed. It's a domino effect, where one unexpected discovery reshapes dozens of interconnected assumptions. This is why Webb's observation is not just about one star, it's about what that star represents, a blind spot in our knowledge that's finally being illuminated. For decades, astrophysicists built simulations and models based on known behavior. Now, a single anomaly is forcing everyone back to the drawing board. In science, that's not a setback. It's a breakthrough. Observations are ongoing. Researchers are closely monitoring the star's brightness, temperature, and spectral lines. They're comparing it to theoretical models and running simulations to determine how such survival could occur. Some are looking into whether neutrino emissions during the original supernova might hold clues, while others are exploring the role of magnetic fields, which could have helped stabilize the core during the collapse. And while the technical work continues, the public reaction has been one of awe. The very idea that a star can survive what should be its final act is poetic and humbling. It challenges not only science, but also the human imagination. It forces us to ask questions that have no easy answers. What else don't we know? What else is hiding in plain sight, waiting for our tools to catch up? The Webb telescope, in many ways, is like a time machine. It allows us to look back into epochs long gone, to see the universe not as it is, but as it was, billions of years ago. But it's also a microscope, magnifying the complexity of celestial objects that once seemed straightforward. A star dies and a new one forms. That was the story. Now we know that the story might have a secret chapter, one we've just begun to read. With each passing month, Webb is uncovering more secrets. Galaxies forming earlier than expected, black holes larger than predicted, and now stars that refuse to die. It's as if the universe is revealing its most guarded truths, one observation at a time. And this is just the beginning. The telescope has enough fuel for at least another decade of operation, maybe more, and every new image it captures adds a puzzle piece to the cosmic mosaic. As scientists continue studying this unkillable star, they're refining their models to explore the strange territory between life and death in stellar evolution. Some propose that these types of stars could emerge under very specific scenarios, perhaps in galaxies with lower metallicity or under conditions where supernova energy isn't evenly distributed. Others suggest that this phenomenon could be linked to stellar regeneration, where remnants of a once-destroyed star slowly reform into a new, semi-stable state. And while that might sound like science fiction, it's entirely possible within the ever-expanding boundaries of astrophysics. The universe has never been short on surprises. Every time we develop better tools, we find more exceptions to the rules we once believed were ironclad. It's a humbling reminder that our understanding is always evolving, just like the cosmos itself. In the case of the star captured by Webb, its persistence offers more than just a scientific curiosity. It's a symbol of resilience written in starlight. Here's something that defies destruction, shining on through circumstances that should have marked its end. It inspires wonder not just among astronomers, but also among dreamers, students, storytellers, anyone who has ever looked up at the night sky and felt small, yet connected to something unimaginably vast. This discovery also opens new doors for technological innovation. Understanding how such stars behave under extreme gravitational and thermal stress can inform the development of future propulsion systems, radiation shielding, and deep space exploration technologies. If we can learn from a star that survived its own collapse, we might one day design systems or habitats that can endure the violent forces of space just as gracefully. Moreover, it reframes our approach to cosmic timelines. If stars can persist through conditions previously thought fatal, their lifespans might be longer in certain contexts. This changes the timing of galactic development, the birth and death cycles of stars, and potentially even the window during which habitable conditions can exist near such stars. Maybe in ancient galaxies, some planets had a longer chance at life than we imagined. Maybe remnants we assumed were dead zones still harbor warmth, light, or even the seeds of new systems. It's all speculation now, but speculation built on data that grows richer every day. Thanks to instruments like the James Webb Telescope, we're not just peering into space, we're listening to the story of the universe, told in light. And sometimes that story includes characters that defy the final act. With every discovery, we learn that space isn't just a vacuum full of rules and relics. It's a living, breathing archive of exceptions, mysteries, and wonders. The immortal star reminds us that endings in the cosmos are not always absolute. Just when we think a chapter is closed, the universe turns the page to reveal an unexpected continuation. We now stand at the threshold of a new era in astronomy, one where the lines between death and rebirth, collapse and survival, are blurred in the fire of distant stars. With each Webb observation, we're reminded that the cosmos is stranger and far more alive than we ever dared to imagine. And that's the story of the star that wouldn't die. A cosmic enigma captured through the lens of our greatest telescope, challenging our theories and lighting a path toward deeper understanding. What else might we discover tomorrow? What secrets are waiting behind clouds of dust, in galaxies unvisited, in light unreceived? Whatever comes next, one thing is clear: the universe is far from finished surprising us.